All right, so let's do a little bit more application with the central limit theorem. In section 5.2, you learned how to find the probability that a random variable x will lie in a given interval of population values. In a similar manner, you can find the population that a sample mean will lie in a given interval of the x mean, so the mean sampling distributions, x bar. To transform x bar to a z-score, we can use the following formula. So it's very similar idea to regular z-scores. It's still the x value minus the mean over the standard error or standard deviation. So here our x values just happen to be the means. Your mean is the mean of the sampling distribution. And then again, your standard deviation is the one of that distribution. So you have that slight change here where you end up taking that standard deviation and dividing it by root n, because we're not just talking about regular examples, we're talking about examples of samples. So repeated sampling over and over and over again, where we have means as our data, not regular data points. So you want to be really careful when you're reading questions here. Your data points are means in these examples, which is why we have an extra step in our standard deviation. All right, so let's find the probability using these sampling distributions. So the figure at the right shows the mean distances traveled by drivers each day. You randomly select 50 drivers ages 16 to 19. So we're looking at this rubric. What is the probability that the mean distance traveled each day is between 19.4 and 22.5 miles? And we're going to assume that sigma is 6.5. So these are the average miles driven by the age groups. So this is the mean here. So for my age group here, I'm looking at a mean of 20.7 miles. Again, this is the population mean. And then here they're giving us the population standard deviation here. Now, notice that what we're doing is we're randomly selecting 50 drivers here, right? So we're collecting a sample, in this case, of 50 drivers. So our n is going to be 50. And we're looking for a probability here. What is the probability that the mean distance traveled? So again, we're not looking at just distance traveled. The mean distance traveled, so everything is in means, is between 19.4 and 22.5 miles. Now, my n is greater than or equal to 30 here. So what this tells me is that for my samples, it's totally fine to use the central limit theorem formulas. And that means my means will also be, oops, that looks terrible, bell-shaped as well. Okay, so when we're sampling, remember that mean of the means is still equal to the original population mean. So in this case, the mean that we're using is still going to be 20.7 miles. So we're still using that same center of 20.7. The only thing that's going to change is your standard deviation is going to get divided by the square root of n. So when you have sampling like this, everything's going to be the same, assuming that you meet the requirements. But we're dividing by the square root of n. So our formula here is the original standard deviation divided by the square root of n. So my original standard deviation is 6.5, and I'm looking at samples of size 50 here, so my n is equal to 50. Now, I have it copied from the book here just because it fit nicely, so we get about 0.9. So the standard deviation in our chart is not going to be the 6.5, it's going to be 0.9. And I want to find the area between 19.4. So let's see, 19.4 will be on the left, so maybe right here, x equals 19.4. And 22.5 would be on the right, maybe right here. Miles, okay? And again, these are mean distances, which is why I'm using x bars here, not just x's. So I'm looking at the area in between. So we want to know what's this area. because that equals your probability, right? So that's really what we're looking for here. And again, this section really tends to throw a lot of students off. But if you think about it, it's actually very similar to what we've already done. It's just that you have a change in your formula for the standard deviation. So if you see a sampling problem that fits the criteria, so your N has to be at least 30 or the original population is normal. So you do need to make sure you fit the criteria. But after that, everything is the same as what we've already done, except for this one change in your standard deviation formula. So that's really the only difference. All the other same techniques we've used are going to come into play here. Now, if you're using technology, this is a good review from earlier sections. We're going to do second bars and use that normal CDF feature. And we're going to put our lower bound, our upper bound, our mean, and our standard deviation. So again, that's your lower bound, your upper bound, your mean, and your standard deviation. Okay, and remember our standard deviation is 0.9 here, right? So that's the difference. But everything else should be the same. All right, so let's review that. So to find the normal CDF, I hit second bars, and then I see normal CDF. My lower bound is 19.4. My upper bound is 20.7. Sorry, my upper bound, excuse me, is 22.5. My mean is 20.7. And then my standard deviation is 0.9. Okay, and this looks pretty good. So let me just make sure I typed everything in right. 19.4, 22.5, 20.7, and 0.9. Yep, so I'm getting an area of about 0.9029 and 4. So I think your book is using 2 decimal places here, so sorry, 4 decimal places. So they round it to about 0.9029. So that would be our answer using technology. Now, if you're not using technology, so here's a good review again of kind of what we've seen so far. But if you're using the table, the first thing I have to do is I'm going to have to convert to z-scores. So if I'm using the table in the back of the book here, I can still set this up. My mean is going to be 0 now, right? So remember, z-scores, your mean is 0 and your standard deviation is 1. And then I need to find this z-score and I need to find this z-score. So I'm going to have to use my formula there. So my z-score is equal to the x value minus the mean over the standard deviation. My x value here is 19.4. My mean is 20.7, and my standard deviation is at 0.9. So for the first one, I should get, let's see, negative 1.41. So this becomes negative 1.41. And then for my other value, I use 22.5. And I get about 1.96. So we are rounding here. So this is 1.96. Now I'm going to go ahead and use the table. So I'm looking for the area here. But you want to remember when you use the table, they give you the area to the left. So it is tricky to use the tables. I do think it's sometimes easier just to use technology here, but we're going to use the tables. So I'm going to go to the table first for my negatives. So I find the negative 1.41. So I have negative 1, where am I? Negative 1.4, and then 1 is all the way over here. So I'm looking at 0.0793. And then my other z value we said was 1.96. So on the positive side, So 0.9750. All right, sorry about all the changing, guys. It takes, like I said, sometimes it's a little bit harder to use the table. Let me just go back to my notes here. Okay, so we just want to be careful when we use the table, the area is always to the left. So this value here actually relates to this area. And this value actually relates to this whole area here. So to find this middle area, I actually have to subtract these two. So I take this one here and then I subtract out the green part and that'll give me the part in between. So I take that 0.9750 minus 0.0793 and what I get is 0.8957 for my probability. So that's going to be my answer if I'm using a table instead of using technology. And you can see that it's pretty close, right? They actually would both, let me see if I get them both on the same page. They would both round to 0.9, right? So again, you do have some slight differences because the tables in the back of the book are already pre-rounded, so they do have some rounding error already built into them, whereas your technology is more accurate. But you can see that they're very, very close, right? They both would round to 0.9. So they're right there. So this is how you can do it using the tables. This is how you can do it using technology. So this is just a nice review actually of what we did in section 5.2, right? So these are the steps that we did in 5.2 where we were given the X values or the Z values and we had to find the areas. So using what we've already learned and now applying it with that slight change to the standard deviation. All right, and let's do a couple more. So the mean room and board expense per year at four-year colleges is $10,453. You randomly select 9 four-year colleges. What is the probability that the mean room and board is less than 10,750? Assume that the room and board expenses are normally distributed with a standard deviation of 1650. Okay, so we're going to assume room and board is normally distributed. So that means that the population here is normal. So the population is normal, then there is no size restriction to use the central limit theorem, okay? So the mean room and board expenses per year at four-year colleges is $10,453. So our population mean here is $10,453. And our standard deviation is 1,650. So again, these are the population values. You are going to randomly select 9 four-year colleges. And we're going to find the probability that the mean room and board is less than 10,750 per year. Again, we're not selecting just one college here or looking at one individual data point. We're selecting a sample. So we have more than one item. We're selecting a sample here. Sample size is 9. So again, a little bit different, right? We're looking at means, right? So we're looking at means, which is part of our focus here, and then we're looking at samples as well. So our N is going to be 9. Again, that's small, but it's okay because the population is already normal, so I don't have a restriction on the sample size. So my mean of the means is going to be the same as the original population, which is 10,453. And then the standard deviation we use is going to be the same standard deviation, but divided by the square root of N. So I use the 1650 over the square root of 9. So 1650 divided by 3 is going to be $550. And again, these means are going to be normally distributed, so we can use that bell curve. All right, so just making my little notes here. All right, the question is asking us to find the probability, and again, probability is the same thing as area, that the mean room and board is less than 10,070. So 10,070 is on this side, right? So it's going to be maybe like right here. So that's going to be x is equal to 10,750. And we want less than. So this is the area that we're looking for. So if we're using technology here, we're going to do second vars, and we're going to do our normal CDF function. And again, we're going to enter our lower bound. Now here I don't have a lower bound, so you're going to use like a negative infinity. So I like to use negative 99999, but any negative large number like that would be fine. Like negative 10,000 is fine, negative 1,000,000 is fine. It doesn't matter as long as it's a very low number. And then we're going to end at 10,750. My mean here is 10,453, and just be careful, your standard deviation is 550. All right, so second vars, normal CDF, so negative. And again, I'm not even really counting my nines there, just as long as it's a big enough number, it's fine. 10, 4, 5, and 550. And when I hit enter, I get about 0.7054, rounding to 4 decimal places there. So about 70.54%, right? So what's the probability that the mean room and board is less than 10,750? About 0.7054. If you're using the table, the first thing I need to do is make it a z-score, right? So this needs to be a z-value instead. So I'm going to take my x value, which is 10,750. I'm going to subtract the mean of 10,453 and divide that by my standard deviation. And just be careful, you're dividing it by this standard deviation, the 550 here. So what I get is about 0.54 for my z-score. Now I'm looking at the area to the left, so this one's a little bit nicer. I can just use the table at the back of the book because they're already set up for areas to the left. Whereas in the last example, I had to actually subtract them to find the area in between. So I'm going to go to my positive z table here. I'm looking for 0.54. So 0.5, and then I'm going to go over to 4, and I get 0.705. So here I get the same exact value, which is nice. So no rounding error in this case with the table, like I had a little bit of rounding error in the last example. So here's how we do it with technology. Here's how we do it with our table. All right, one more example. Some college students use credit cards to pay for school-related expenses. For this population, the amount paid is normally distributed. Okay, so the amount paid is normally distributed. So we're told that our population is already normal. So if your population is normal, then the sample size is not an issue, right? I don't have to have a minimum sample size. Sorry, let's just say with a mean of 1615 and a standard deviation of 550. All right, so let's make some notes here. My population mean is 1650 and my population standard deviation is 550. This is for the population. All right, part 1. What is the probability that a randomly selected college student who uses credit cards to pay for school-related expenses paid less than $1,400? And remember, probability and area on the graph are the same thing. So we're looking for the probability here. Now, be really careful because we're mixing it up. Notice the question says that we are randomly selecting a college student, a randomly selected college student. We're not doing a sample here. We're taking one college student, right? A college student. So if it's not a sample, it's a regular problem. So you don't want to start mixing up your regular rules with your sample rules. So if it's a regular problem like this, we're going to use our regular old techniques. So I'm going to draw my graph first. Okay, so my mean is 1615, and my standard deviation stays the 550 here because I'm not doing a sample. I'm not changing the standard deviation. It's a regular problem. and I want a cutoff value of 1400. So that's probably around right here. And I want less than. So I want to find this area right here. Now for this last example, I'm just going to use technology. If you want to see it with the z-scores, your textbook actually does it with the table instead. So you can check out that in your textbook on page 268 and go through the steps there. I'm going to use technology for this one because again, I think it's a little bit easier actually. Not only is it more accurate, but I do think it's actually easier a lot of times. So I'm going to use technology and we're going to hit second bars and we're going to use that same normal CDF. So my lower bound here, again, it goes for forever. So I'm going to use like a negative infinity idea. So just some sort of really small number going up to 1400. My mean is 1615 and my standard deviation is 550. Okay. And I get about 0.3479. So let's see, okay, how about your book use 4 decimal places? All right, 3479. So I'm going to stop there, round to 4 decimal places. And this would be our answer here. Now, if you actually use the table, the book got 0.3483 with the table. So again, you see some slight discrepancy there, but very, very close. And that's just due to rounding error. So this would be our answer. And again, if you want to see the z-score process using the table, check out your text to see how to do it that way. Okay. Now our second question, you randomly select 25 college students who use credit cards to pay for school-related expenses. What is the probability that their mean amount is less than 1400? So look at the difference in the question. Here, I selected a college student, and they specifically paid less than 1400. Here, I'm selecting 25 college students, and their mean is less than 1400. So now we have one of those sample problems, right? I have more than one person, and I'm talking about means. So, and notice that it is only a sample size of 25, but the small value doesn't matter because my population was normal to begin with. So the mean here we're going to use is still the 1615, but the standard deviation is going to change now. It's going to be divided by the square root of n. So I'm going to take the 550, I'm going to divide it by the square root of 25. So 550 over 5, which is going to be 110. Okay, so again, I'm just redrawing my picture. Again, noting my standard deviation has changed this time, right? Because now I have a sample, so I have a slightly different setup. I'm still looking at that 1400 though. So my picture is going to look pretty similar, but I'm going to get a different answer because my standard deviation is different. So again, I'm looking here, the x is 1400. I'm going to use my calculator here too, but your book does use the z-scores. So feel free, if you're using the table instead, go ahead and check out your textbook. Notice I'm setting it the exact same way as before, but now my standard deviation will change. I'll put in the 110. So normal CDF. Type in all my values there. Hit enter. Oh, I must have done something wrong. What did I do? Oh, I hit the wrong function. Inverse norm. Whoops. Sorry, guys. Sorry. Normal CDF. I apologize. I couldn't see the screen. This angle. Negative 99999. Make sure I don't do another mistake this time. All right, that looks better. And then I get 0.0253, okay, and that looks good for our decimal place here. So your book's using 4 decimal places again. Now, if you're using the table, they got 0.0256. So again, some slight differences if you're using your z-score first and then going to the table, but very, very close. And usually my math lab allows for a little bit of wiggle room like that on these questions. If you're having issues, they'll reach out to me. So again, just watch really like this question here because it shows you what to watch for, right? The first question is a regular problem. It doesn't say anything about samples there. We're selecting one student. It doesn't say anything about the mean. It's just that one student pays less than $1,400. In the second example, we're selecting 25 students and we're talking about their mean amount paid. So right there, I have two flags that say that I'm using a sampling distribution here instead. So the sampling of the means for the distribution. So it's going to change my standard deviation. We still need to check the background, right? So here my sample size is only 25, but because the population was normal, it was fine. So you still need to check that requirement to make sure you can use the formulas. But we're just going to change that standard deviation, and that will, again, fix it. So last step is just to compare the two probabilities. Obviously, this one is much smaller here. So when you use this sampling formula, you are dividing your standard deviation. So it's just squishing those means together into a much tighter bell shape. So you do have much less variation there with that. So although there is about 35% chance that a college student, so almost 35% chance of a college student that uses a credit card to pay for school-related expenses will pay less than $1,400. There's only about a 3% chance, so this is about 2.5%. So the second answer, about 3% chance that the mean amount of a sample of 25 college students would pay less than $1,400. Now that second value is only 3%. It's less than that 5% or 0.05 cutoff. So actually this would be an unusual event, right? So even though this is not unusual, to get 25 students whose mean was that low is unusual. So you saw that same idea of the cutoffs being 0.05 for unusual versus usual events. All right, so one last thing I want to note, and this is just kind of like a side note here, I've been thinking about as I've been going through this lecture. For those of you using technology, you're gonna use this normal CDF function when you know the X value or Z value, and you are finding the area or probability. That's what we just did. Sometimes students mix that up with the last section of the text. So we use the inverse norm function when we know the area or probability and we are finding the X value or Z score. So you just want to make sure you use the right function if you're using technology, and students mix this up a lot. So you use the normal CDF function like we did here when you know the area, when you, oh my God, see, I said it wrong. When you know the Z score or X values and you're finding the area. So in all these examples, we were finding, right? This was our question, what is this area? So you're using normal CDF. You use inverse norm when you're working backwards. So you already know the area, but you're trying to find on the cutoff mark, the X or the Z value. So you just want to be careful because those are really easy to mix up in the processes. So you want to make sure you have the right procedure. Are you finding the area or are you finding the X value, right? Or Z value, so that you're going the right direction with that technology.